connectivity, and I will invite first Jim Cowie of Internet History Initiative. So, what's your presentation about, and do you have a presentation to show?
Okay. Is this live? This one. Okay. Still working. Okay. Very good. Thank you very much. I'm Jim Cowie. I'm with the Internet History Initiative, and I'm a research fellow this year at the Berkman Klein Center for Internet and Society at Harvard University. I thank very much the local organizers and Right NCC for the opportunity to come in and present a little bit of the story behind what I've been doing this year. The year is only 2 weeks old. So what I'll be showing you is some very fresh research, some partial stories. And to complete these stories, the reason I'm here really is to talk to the local operations community and complete the story. So this is work in progress. The Berkman Klein Center consists of digital scholars of digital society in general. And so my job this year is to serve as kind of a translator between internet measurement, this long history that we all have of collecting information about how the internet was built and how it functions, and putting it in a form that other people's research can incorporate. So telling stories is really important. And I'm focusing on understanding how the internet has evolved regionally. And so if you've seen my presentations from 10 years ago, they would often be about specific providers, specific countries. Here I'm going to zoom out a little bit and tell some partial stories about regional performance for this region. Clicker not working. There we go. So because I am no longer with Renesys, which ended a long time ago, I have to use wonderful data from folks like the RIPE Atlas program. RIPE Atlas, as Hans Petter said, has over 10,000 probes distributed worldwide. This is kind of a map at log scale. So the densest hexes here have hundreds of RIPE Atlas probes. The lightest ones have just a few or maybe just one. But it's a wonderful network. And please understand that if you participate by hosting these RIPE Atlas probes, particularly in networks that don't have any yet, you're not only helping us measure more accurately and helping your own measurement projects and understanding, but you are also being a huge help to the research community and trying to understand the patterns of how this works. So I have two experiments, partial experiments today. The first one is a look at regional latency trends. So the part of internet history that concerns how long it takes to get from region to region, which is a critical part of the story. And then second, we'll look at the particular instance of DNS Anycast and how that gets mapped worldwide and into this region in kind of connectivity watersheds. But I'll start with the latency trends. So here's what I did. I took all of the, oh, thanks, I took all of the Atlas ping measurements on a particular day. In this case, this is 1st of August. And I did it each year, going back through history, because the RIPE Atlas history is wonderful and goes back a long time. We're measuring from all the probes worldwide to all of the anchor probes that are here in Central Asia, meaning all of the countries combined. And what's interesting then is we compute a density estimate of latency. So latency here is on the x-axis, and a density is a peak in the spectrum. So it's kind of dominated by geography, as you might imagine. There's a small peak here, which is Central Asia talking to itself. That's about less than 50 milliseconds, as you'd expect, thanks to good local interconnection. There's a large spike for all of Europe. There are smaller spikes for getting to the US, getting to the US West Coast, getting to the Middle East, and getting to East Asia. And there's kind of a long tail. As you go beyond 300 milliseconds, these are the really long paths that go all the way around the world. There's a small inset on the right. The thing on the left is IPv4. On the right is IPv6. They have kind of the same shape because they are dominated by geography. What you'll see in the IPv4 plot is that there's some difference in the last couple of years. In 2023 and 2024, there's some energy coming back from the long part of the tail and increasing the peaks in the spectrum for these closer peaks. So this is part of what we try to understand. So to tell the story about regional trends, if you've ever worked with the Atlas data, you know that it's really detailed, huge volumes and very detailed, probe by probe. These things measure and ping continuously every day. And so to boil that down, we need a filter. So the model we use is to make simple rectangles, and we'll pick out 7 regions of the world, and we'll basically lump all of the probes in that area into kind of a single class. And we'll measure the latency from each of these regions into Central Asia. It's round trip, so it may not be symmetric, but we're going to count the total latency. And these regions are presumably what you might be looking at if your customers here want to reach markets overseas, might fall into one of these 7. So here we take each of those categories, take all the probes, we boil them down to a single number per day, which is the median latency on that day from that region to this region. And if you look at the left side, it looks about like you'd expect. There's sort of a geographic sorting. Central Asia is very fast. East and West Europe in green and gray, followed by the East Coast of the United States and the Middle East, presumably going to Frankfurt and coming back to the Middle East. Then the West Coast of the United States in pink. Then South Asia, meaning broadly India, in purple. And finally, East Asia, the slowest one, the longest path at more than 300 milliseconds. And then the nice thing about this graph is on a particular day, things change. And that day was really a 2-day period in February of last year, where we see East Asian median latencies in particular change and improve quite a lot. They come down from a median of about 320 to about 230. And then as time goes on, we get into the summer of 2023, they improve still more. Now they're about 190 milliseconds. And other things are happening, and you can see it gets a little chaotic, but this was the primary interesting change. So to dig into that a little bit, this is a level of detail that I might not share as a storyteller to a non-technical audience, but you understand this really well. We took a look at all the trace routes in a week before that change and all the trace routes in a week after that change. And look at the last foreign router, in this case, in traces from East Asia to Kazakhstan in particular. Who owns the last foreign router before we get here? And in the old days, where latencies were very high, they are almost universally Russian carriers. Right? We've got Vimpelcom, Transtelecom, Rostelecom, ER Telecom, Kvant. The shift happens. A couple of weeks later, we take another look. And what's interesting is now there's a lot of PCCW. Right? This is old Hong Kong Telecom. This is the Kazakh border router in Hong Kong. And there's also then important routers, the penultimate hop from Google and from Amazon Cloud in Korea. Pretty interesting, right? These are how the probes are now reaching this region in their preferred traces at the lower latencies. So the shift is actually really nice. If you take a look year on year, August versus August, green here says that the latency's improved to a lot of East Asia by maybe 100 milliseconds in median. Other parts of the planet are kind of unchanged, maybe a little bit worse to the Middle East. But this is quite a distinct shift as part of the story. If we dig into it furthermore this year, so just since January of this year, the situation continues, and we get one more piece of information almost by accident. We get the Simiwi 5 cut in the Strait of Malacca. And when that takes place, you see latencies to the east, to East Asia, the yellow or orange line increase slightly. To the Middle East goes up quite a lot, which is interesting, right? Why would a cable cut in the Strait of Malacca affect transit between here and the Middle East? And everything else is pretty much stable. You can also see an interesting 1-week period here where the story reverts to the previous story. So I say story, sometimes we would say mode. There are modes of connectivity here, and we start to recognize them. This is the characteristic mode. It goes away because of engineering. Something happens, interconnection changes, and the old story comes back for a period of time, but then it reverts. So by getting familiar with these changes is how we would think about making this work out. Here's just a specific example I grabbed of, this is a probe in Guangzhou, China, trying to get to the Kyrgyz internet exchange here in Bishkek. And looking at the latency mon tool, you can see that this is one day. Actually, I think this is a day last week. You see both modes present on a given day. You see the very long mode, and you see the very short mode. In the long mode, traffic is going around the planet through New York to get from China through New York to get back here. But then later it improves. We get the other mode, which is going through China Mobile International and arriving here. So it's interesting, right? This is part of the story that we want to tell. This is it's inconsistent, but this kind of shift is a major shift in the way that we see the region interconnect with others. And I think we'll see some more in subsequent presentations about the possibilities there. For now, though, let me just quickly move on to the second experiment I did, because it's also interesting. I did an experiment at CAPIF1 where I manually looked at the distribution of 8888, Google's Anycast DNS, manually trying with my own authoritative server, trying to figure out where Google was mapping different people through. And what I realized only this year by talking with the RIPE team was that they actually have an experiment like this. And RIPE Atlas is very much like this. There are so many different experiments in this system that you can go back and discover that people have been running in some cases for years. Beautiful data. In this case, there was an old hackathon several years ago, more than 5 years ago, where they did exactly what I did in my CAPIF1 presentation. They started asking a question of an authoritative Google server and another one run by Akamai that basically says, what's my IP address? So what you get, the answer is the IP address of the last resolver that asks the final question of authoritative on behalf of the user. And for Google, this is quite interesting because they publish lists of the unicast addresses that they are using for their different data centers. And so we can go in and map it out. There's a trend here, right? Which is that in this hackathon experiment, they didn't specify any particular recursive resolver. They just wanted to use whatever was set up for the local probe. So typically that would be in your own autonomous system, right? You run your own DNS, there's your recursive. That's kind of the classic pattern. In this region, back in 2017, 2018, fully 50% of all of these queries were coming out of your autonomous system. You were running the resolver and you were asking the questions of authoritative. That has declined over time, as what has risen is the role of Quad 8 and other Anycast DNS providers. In this case, Google has risen from maybe 10 or 15% of the probe set here, of the query set here, to being more than 35%. And on the right, you can see that it's more in Kyrgyzstan, Kazakhstan, it's less in other regions. What share of queries from Atlas probes tend to go to Google? But it's a fairly substantial level. The reason that this is important, and I'll move a little bit quickly here, is this is what Google does. Google tries to steer queries to their favorite data center to try to make latencies low. This is how they do it in North and South America, for example. You can see that queries are getting mapped pretty close to where they are. So Oregon, if you're in the middle of the United States, you go to the Iowa data center in the middle of the cornfields. Wherever you are, you've got one close by. In Europe, it works slightly differently. In Western Europe, it still works like that. They map you to very, very close. The Milan data center will serve all the way down into Turkey, perhaps, maybe as far as the Caucasus. You'll see Iranian probes actually being served from Frankfurt, but mostly it's very local. And the obvious exception here, in kind of the grayish brown color, is the Russian-speaking world. Google basically maps everybody in the Russian-speaking world to one data center in Finland, which I suppose makes some sense. But as you can see here, Russian providers all the way into Crimea, the Russian transit customers here in Central Asia, all the way out to Vladivostok, it's all going to Finland at relatively high latencies. Is there a better solution? I don't know that there is right now. Based on the previous discussion where we showed that latencies are dropping to East Asia because somebody here is attempting to improve the quality of experience with internet counterparties in East Asia, it's possible that someday the Hong Kong point of presence for Google or Tokyo or Singapore could be plausible alternatives. But I leave that for another day. So thank you very much. Again, these are partial stories. I appreciate talking with you at the break about ways to complete this.
Thank you very much. It is actual informative presentation.